All right, and so now we are ready for vertical scaling of a graph. And so here I'm calling that vertical scalings. So because there are different ways how we can vertically scale the graph of a function, and I will quickly demonstrate that as following. Okay, so this is exactly what it means by vertical scalings right here. So now on my graph, on my empty graphing screen right here. So this is the graph of some function, okay? And knowing what exactly this function is at this point is not important. But now with this function, let's say we want to bring that function, all right, and so now turning that into a blue version right here, a blue color right here now. I'm going to turn that function, okay? So this is some transformation. So vertical scaling is in a sense that if I'm using the guiding points, these are the guiding points for the original graph. And now this is the points for the transform graph. So if relative to the parent function, then you can see that these points are being vertically scaled up higher. Okay, so that's what I'm calling that vertical scaling right there. Or the same thing about the same point right here. Let me put these back in the original spot. But now we can scale it down so that the graph becomes vertically shorter. Okay, it's become vertically shorter or vertically stretched up. Okay, and so stretch or compressed, yes, that's a term that those are the terms that are commonly used by many professors. But then to me, allow me to explain all of those as just generally the vertical scalings. So either we're stretching it up, okay, or we're compressing it down shorter to make it a shorter graph. So the same shape right there again, but being in a shorter version vertically, or being the higher version vertically right there. And that's what the vertical scalings is all about. And then furthermore, we also want to study what causes the graph to flip upside down. Okay, vertically flipped. Okay, through the x-axis, and once vertically flipped, it continued to become vertically stretched downward. Okay, vertically stretched downward. So in the end, all of these events that happen to the graph, any of these events that happen to a graph, I refer to that as a vertical scaling. Okay, and so these events, informal math term, we call them these are one kind of transformation. Okay, so that kind of transformation I regard to that as the vertical scaling. So different ways how we vertically scale a graph here. All right, so now let's dive into learning about what cause these vertical scalings right here. Like, and you have seen in my demonstration earlier that it was either being pulled upward, right, stretched vertically up, or compressed vertically, or being flipped through the x-axis, okay, to turn upside down. Okay, and then continue to be stretched further down right there, or compressed. We're gonna study all that. Okay, so now on my board here, in this way of what we're looking into, allow me to, and at this point you have picked up quite a few terms in my teaching style. So I've caught some of you, at least you have heard from the previous kinds of explanations that I've used the term the parent function, or and then the child or descendants function. Okay, and then I've also used the term the guiding points and all that. So guiding points is just my own term for this kind of problems like that. Okay, so now gonna start out with a function again. So I'm gonna say let f of x be the x squared function. Okay, let f of x be the x squared function. And so now, so here, as far as the relation, as far as being a parent function, yes, for the parent function. And again, I'm using that. I set up this convention of mine. The parent function is being in red ink right there, and then any of the descendant function is going to be a function that's eventually graphed in blue. Okay, so yes, my intention here is I'm going to call this function f of x as being the parent's function. And so now I am going to define a descendant function as following. Okay. All right, so we're going to define a descendant function. And now allow me to introduce that optional plural right there. So let me first define a descendant function as following. H of x here, how about I'm going to define that by 3 times x squared. So g of x as a descendant function is defined as 3 times x squared. So again, just like how I explained that back when we were still looking at the vertical shifts, then g of x, or as being as a descendant function, being a descendant function, it's already a completely different function from the parent function. Okay? Any child is different from their parents. But then in the end, there is some relationship between the descendant function we're looking at here and the parent function. So again, so very similar to how I have seen it. What I recognize here is that this g of x is defined as, so hey, wait a minute, this x squared right here, isn't that it's the parent function right here. So in the way how I see that now, g of x really is defined as the parent function, but multiplied by a constant 3. Okay? And now at this point right here, this parent function here, allow me to just underline that to turn to have your attention specifically focused on that. Okay, so that's the parent's function. And so now, once I realize this, now let me put in a little note right here. So this is called a coefficient. Okay, or now also quite a few times you will hear me calling that it's a scaling factor. You will understand what exactly it means by calling that a scaling factor as we progress through the lesson here. But now this scaling factor or this coefficient here, which we multiply entirely to the parent function, this is just observation right now. I see that this scaling factor is a value being positive. Okay? And furthermore, it's not only just positive, it's positive and it's greater than 1. It's a value that's positive and greater than 1. So positive for sure and greater than 1. And so needless to write the two of them. See, it's positive and it's greater than 1. But eventually, logically combine these two inequalities together, all we have to say is just simply the scaling factor I'm using here, or the coefficient I'm using here in this problem that defines g of x is, as an observation, is value being greater than 1. Okay, so of course it's greater than 0, being a positive value. So let's quickly have a look at what happened when we have a parent function, when we define a descendant that's related. So here is the relationship between the dependent function, the descendants function with the parents. Okay, and so in that way, it's very similar to how I have explained about the vertical shift. And now let's see what this does. Okay, let's see what multiplying a constant to a function, specifically the greater than 1 constant right here, multiplying that to a, let's see what multiplying that constant to a function will cause to the graph of this parent function. All right, and so now on my blank graphing space again. Yes, ladies and gentlemen, this is the graph of the parent function. This parent function is and I purposely did use this parent function. It's one among the toolkit functions. It's one function among the toolkit function. This is called the basic, the simple quadratic function. Okay, so that's the function for the f of x and written in red. And so now let's quickly, I'm going to use my graphing technology, and you can do this along too. I use Desmos, and just like how I explained when I was explaining about the vertical shift, I use most of the time Desmos, but it should be working. There should be similar functionality in your standard TI 83 or 84 calculator, and I've had lessons showing you how to graph. So here you just simply pull out your technology and graph this function. And so to see the result, I recommend graphing the parent function and graphing the descendant function in the same graphing space so that you can start noticing, okay, and we can start making some observations about, you know, the changes between the parent function and then the descendant function. Okay, what traits from the parent function that can still be carried to the descendant function? Okay, and then what caused the change? Because like I said, every child is different from their parents. Okay, so now let's get to it. So again, on the graph here, you are seeing this is the graph for the parent function, the simple quadratic function. And now also earlier when I was still explaining about the vertical shift, I start bringing in, and that was my own terms, I believe, but I start bringing in the term that's called the guiding points, or the setup guiding points, because any graph, see, look at the way how it is. Any graph here, we can decide a few guiding points. Those are simply just the points that stays right on the grids right here, making it easier to notice the changes when we're doing the transformation. So for this particular graph, the simple quadratic function, the guiding points are these points right here. Okay, and those are not the only points, but just within these 5 points, those are good enough. Okay, or maybe I can also put in some, see, we can have another one that happens at x equals -3 with this value right here, so -3 comma 9 right there. Okay, and then we can have another one at x equals 3 right there. Okay, so it's 3 comma 9, and so these are the labels for the guiding points. Okay, so now and for a spacing purpose, I highly recommend to hide away, for now I'm going to hide away the labels of the numerical labels of each point here. Okay, so these are the guiding points. And so now I am going to quickly graph the graph for g of x. So now this is g of x. Okay, so fundamentally g of x has the exact same shape, and that's the trait where this descendant has carried over from its parent. Okay, it still has that shape, but then it already has some difference. Okay, so what's that difference? It seems like this graph here is thinner. Okay, but then thinner is going to start making people think about horizontally being pressed in, but that's actually a deception right there. So now how about let me put your put your focus in a different way of seeing it. So how about I'm going to also put in the guiding points for this. Okay, those points that stays right on the grid. So how about when on the grid when x equals -1, okay, then the y value is way up here. Okay, now for the parent's function, when x equals -1, the y value was at +1, but now on this descendant's function right here. All right, so now let me put in the, all right, so that's the set of the equivalence guiding points. Okay, but then on the descendant's function. So now I noticed that now it's also a good idea now to put in the labels. Okay, at this point. All right, so for now let me zoom it in a little bit. So for this guiding point on the original parent function, when x is the same line, x equals -1, that's transform points which now belongs to the descendant function. It's still on the same line, x equals -1, but now the vertical value becomes as high as 3. Okay, no longer 1. So on the parent's function, the y value is 1, but now on the descendant function, the y value is 3, and still we're on the same x value grid. Okay, so let's look at so now this other point is being hidden outside of the viewing window. So now let me zoom it out a little bit. But what about when it's when x equals -2? When x equals -2. All right, so when x equals -2, our point on the parent function is 4 for the y value. Okay, so when x equals -2, our y value on the parent function is 4. But then on the descendant function, same grid line for x equals -2, but now it's 12. All right, and so now let's look out for the other values right here. So what about this one right here? All right, so x values on the same grid. For x value, it looks like y value of the descendant function is 3 versus 1. Okay, and now on the same grid for x right here, when x equals 2, the parent function has the y value equals 4, but then the descendant function has y value equals 12. And now I start noticing. So after observing the graph, I see that the y value. So I purposely point you to the same x value. So it caused no change to the x value on each of the points on the graph. But what happened? What we saw there. And now let me put that graph back in the middle of the corner of the board right here, so that you can still see along. But on each x grid right here, the value of the y value on the descendants graph seems to be about 3 times higher. Okay, 3 times higher. And again, everything I'm saying here is based on the constant here being a value that's greater than 1 for now, greater than 1, and so of course it means it's a positive value, and furthermore being greater than 1. So what we observed there is the g of x, the graph for g of x, every point equivalent to that point on that parent function is being now 3 times as high. Okay, 3 times as high. All right, so we've got something so far. So it looks like, so now just let me write it down, that observation right here. So it looks like, okay, it looks like every y value, right? Every y value is 3 times as high. All right, and high, I mean vertically pulling it up and vertically scale it up. That's why I'm using that term 3 times as high right there. All right, so now we start having a good sense about what caused a vertical scaling right here. Because being 3 times as high, 3 times as high what, of course, compared to the parent function. Okay, so 3 times as high. So where did that? So observation came out with 3 times as high because we stay on the grid. So now that's making it consistent with this constant 3 over here. Okay, but let's not rush. Okay, let's not rush. Let's run into another kind of problem right here. So now I'm gonna write down another descendant function. And so now I'm gonna have to erase this. And now we can call this h of x because it's a different function. Okay, h of x. But now how about I'm gonna define this as a 1/2 x squared. Okay, now sometimes this can be written as an x squared over 2. So algebraically, x squared over 2 is exactly the same as 1/2 x squared. Okay, but for the purpose to see the transformation and to see the relationship with the parent function, instead of writing x squared over 2, I write it as a 1/2 x squared. So that's just something for you to realize. Okay, and that's why when you arrive at a course like this, you have to master your skill already and be fluent with seeing these different forms of how you can express a fraction. Okay, and so now I don't need to write it like this. So 1/2 x squared. The parent function is still here. It's the x squared. So wait a minute. I see this overall h of x function, and again, it's a completely different function already. Okay, it's different function, but it has this x squared here, which I now recognize as this is where the parent is. Okay, this is where the parent is. And so what makes it different is that this function is the parent function multiplied with a constant again, or a coefficient value. Okay, so how I see that? This is how I see it. H of x, and that's why I call it, it's another descendant function. It's similar to the g that we've had. It's not the same function with the g either. It has this 1/2 scaling factor. It has this 1/2 coefficient and multiply with. So what I recognize is the parent function, and the parent function is this f of x. So as a matter of fact, now we realized that h of x is defined as simply the same parent function f of x, but just multiplied by a coefficient 1/2. All right. So So you can see that this is sort of like a sibling with the g of x I introduced earlier. But of course, so you are different from your sibling, okay? No brother and sister are exactly alike with each other. So just like that, even though the h of x here and the g of x I erased already are siblings, but they are in the end, two different functions. So what makes the difference? They're all having their parents in them, okay? They're all having their parents in them, being multiplied with that parent function. But then this one here is only is multiplied. I mean, this one here is defined by multiplying the parent function with a 1/2 coefficient. So what about that 1/2 that we have noticed here? What about that 1/2 that we noticed here? The 1/2 is still a positive value, okay? But then this 1/2 here is indeed, this time is less than 1, because numerically 1/2 is about a 0.5, or exactly a 0.5, if anyone think the numerically as, as decimals, right there. Okay, so 1/2 numerically is a 0.5, so it's less than 1 for sure. But still, in the end, this h of x and the g of x earlier, these are all the kind of function where we multiply the parent function with a coefficient, with a positive coefficient. Okay, so let's see what the graph of this gives. Okay, and I'm going to use a graphing device again. Okay, and so for here, since we're completely studying from scratch, so this is where graphing device is extremely useful for us. Otherwise, we're going to have to construct table of values and get values in, which, back in a long while ago, it was how I was raised with when technologies were not all available yet. Okay, but now we can let technologies come in and be a good assistance for a purpose like this. Okay, and so now I'm going to define that. All right, so here we go again. This is our graph of the parent function, the x squared function, the famous x squared function. And I already put all the guiding points here. All right, so now I am going to put in the graph of h of x this time. All right, so this time here, the graph in blue now is the graph for h of x. Okay, and so as first sight, it seems like h of x is a fatter version, okay? And I'm kind of doing that motion right here, fatter version. So it looks deceiving at first, because when I'm saying fatter, it seems like the graph is being horizontally stretched out. The two sides of the graph are being pulled out so that it becomes a more widely spread out graph. But as a matter of fact, that's only a deception. Okay, so now let me put the guiding points on the blue graph as well, and we will notice the actual change. So back on the graph in full screen view right here. This is now the set of all guiding points on the blue graph right there. All right, so let's have a closer look. So now I can zoom in much further in so that we can notice. All right, so let's now look at these 2 points right here. The one in red, pay your attention to the one in red right here. This is from the parent function. So on the parent function, this point right here, and of course on that same grid lines. So they're all, the parents, the points on the parent function and the corresponding points on the descendants function, they all stay on the same x value grid line right there. Okay, so now let's look at that grid line x equals -1, this line right here. And so what I see here, x equals -1, but y equal +1 originally on the parent function. But now on the same grid line for x, the y value here came down to about, and the coordinates is being explained right here. Okay, 0.5 or a 1/2 for the same x value grid line, x equals -1. So we start sensing something, we start observing something, we start seeing something. And then it becomes even more, the story becomes even more clear when we're looking at these 2 points. This point on the parent function at the grid line x equals -2. The y value here on the parent function was at y equals 4. And now on the same grid line, when it came to the descendants function, h of x right here, then same grid line, that's why -2 is first in the pair of values. But then now, comma 2. So the y value here is only halfway, half the height, okay, half the height. All right, it's only half the height of the original height right there, half the height. All right, half the height. So a different way of saying that, half the height. So now that's what I noticed, and you can, I'm still leaving that graph at the corner of the screen right here. You can check it out throughout the other points, but now I start of noticing something. Okay, so for h of x right here, it seems like what we noticed here is that every y value, okay, and again, nothing changed about the x values at all. All of the x values seems like it stays, those stays the same. So every y value is halved, okay, this is in daily term right here. Every y value is halved. But really, half, that's just a daily language term, but half means, so every y value is 1/2 times, okay, 1/2 times as high, okay, 1/2 times as high. It just means what, from compared to the original height, this height now from on the descendants function is only half as high, okay, it's only halfway as high. And so now where do you think, okay, this 1/2 coming from? Take a moment to think about that. All right, so yes, if you recognize and agree with me, that's 1/2 comes from this factor that we put in front of that function. Okay, so now that came out as an observation. So let's double confirm our understanding so far. So now if we multiply with a 1/2, it seems like every y value is 1/2. So if it's a 1/4 here instead of 1/2, then does that mean it's only going to be the height of 1/4 for every y value? Well, let's quickly check it out. Okay, and the graph is still here on the screen, and now I'm going to bring that into the full screen view right here. All right, so I brought up that little question earlier. What if that scale, what if this was a 1/4 right here? Would that mean every y value is quartered, I mean is divided into fourths, okay? Or only a fourth of the as height, okay? So let's find out. All right, so now I change. So now this is, ladies and gentlemen, this is the graph for h of x equals 1/4 times f of x, if that was the one that we brought it here, okay? So if that was the one I brought here, if this was a 1/4, if this was a 1/4, then yes, have a close look again. If that was a 1/4, then every y value, okay, so when x equals -1, the y value is 0.25. It's only 1/4 of the original y value on the parent function. If x equals -2, the y value now is 1. It's only 1/4 of the original y value, okay, on the parent function. All right, and so now we are more firm with this result that we have confirmed on this. So what happened here is that this function here is defined as the parent function multiplied with a positive coefficient or positive constant, but then the constant there itself is below 1. It's less than 1. So many textbooks writing this, many textbook authors write this as a, 1/2 is less than 1 but greater than 0. That works too. That works too. All right. So that's how I'm seeing it so far. So now I'm going to erase out h of x. I'm going to erase out this descendant right here. Let's look into another one. All right. Okay, so what about, now I'm going to define, and eventually I'm going to be running out of letters. So let's call that j of x, okay? It's a different function's name. And now let's call that, how about minus, okay? Minus two x squared. Minus 2x squared. Minus 2x squared. So, in a way how I'm seeing this, it's a descendant function. It's not the same as any of the earlier siblings I brought up. This is here, but it still has that parent function component here. F of x, or you can just simply verbalize it out. This is the parent function. And so how I recognize that here is really j of x. Okay, j of x is the parent function, f of x, multiplied with a coefficient -2. So now let's bring in some observation. Or let me put in my own observation for you to catch pay attention to that. But the observation here, at least from me, I see that this coefficient, it's in pretty much very similar situation with the earlier siblings like that as well. So far, this is the third sibling I brought up for here, but they're all about the parent function multiplied with a coefficient. And earlier we were working with positive coefficients, and then we investigated even a little more detailed, positive and then above 1 and then positive and then, but still below 1. But now it's a negative coefficient multiplied. So now -2 is negative. Okay, and furthermore, -2 here is even lower than -1. Okay, lower than -1. All right, so let's find out what happens. Let's find out what happened. Okay. So, all right, so this is now the graph for our parent function again, and these are the guiding points that I'm putting here. Okay, these are the guiding points. And now, let me now put in the graph of j of x. All right, so the blue version here is j of x. So, the first thing that caught my attention already, that same shape there, now being brought downward, being flipped. So now this descendant here is a flipped version. Okay, it's a flipped version of the parent function that you're seeing. Okay, the parent function is still in red that you're still seeing on the screen right there. Okay, but this time now the blue one, this descendant j of x, it still has that parent in it. Okay, that's why it's in that same shape, but now it's flipped downward through the x-axis. You can see that. Okay, and then so putting the two graphs together, you can see that a little more clearly right there. So really, what caused that flip right there? The negative sign. Okay, so the negative sign of your coefficient is what caused that to flip. Okay, and now having that flipped, but furthermore, aside from being flipped, so now notice this -2 is less than -1. So another way, and if I want to drive your attention into this way of understanding, but -2 being less than -1 in the way how I see it. I mean, also there are many professors seeing this too. Okay, but that means absolute value of this, because the actual coefficient is -2, but as an actual value, as an actual scaling, we put that in absolute value, it's greater than 1. Okay, because absolute value of -2 is a +2, it's greater than 1. Okay, what does that do right here? All right, so now let's look back at the graph in full screen view, and this is what I'm trying to explain right here. All right, so now let me put in the guiding points. All right, let me put in the guiding points. So now let's just focus on these points right here. The parent function is still here, and on the, again, let's focus on the same x grid lines, the grid lines for the x value. So when x equals -1, for example, the parent function was +1, okay, and that was pointing up. That's why it's +1 for the y value. But now on the descendant function, now it's -2, -2. So negative made it turn upside down, just like how I already pointed that out. But now, what caused it? What made it vertically stretched far? So it stretched by a distance. It's got stretched by a distance of about 2 grids below the x-axis. So here, 2 grids scaled down. Whereas on the parent function, this point is only 1 grid vertically away, 1 grid vertically away from from the x-axis, but now the descendants here, yes, we know now that it's turning down, but we also know that it's 2 grids turning away, 2 grids being scaled away from the x-axis, okay? And then let's look at how about x equals 2 on this grid right here. The y value was 4, okay, being 4 grids away, vertically away from the x-axis. But now look at this one right here. It's -8 on x equals -2 grid right here. The y value is -8 on the descendant function. Okay, so it looks like, well, as far as negative of this value, it's explained because we had a negative coefficient. We already knew that, but now in the way how I'm seeing it's 2, 4, 6, and 8 grids, again, vertically away from this x-axis. All right, and that's why, you know, counting that strictly in terms of how many square grids away from this axis right here. Okay, that's why I'm putting that systematically as, you know, the absolute value of your scaling factor, absolute value of your coefficient. So what matters is, so this is the scaling. It's being twice as large. It's being twice as high, but then it's going to be flipped down. Okay. So now let's put that. Let's put all of that observation together here in a statement. So every y value, okay, is 2 times, how about this time, let me use the term farther, okay, 2 times farther. And I demonstrated earlier, farther away from the x-axis compared to the original parent function. But then furthermore, okay, flipped downward. All right, so that's the observation. So now we start putting into our understanding, anytime we have a negative coefficient, it will cause a flip, okay, a vertical flip, a flip of our graph, a flip from the parent function through the x-axis. But then furthermore, after being flipped, okay, and then upon being flipped, it's going to be scaled as much, 2 times further compared to the original y value on the parent function. All right, and so now I'm going to erase this descendant function. We have looked at the third one so far. All right, so now let me introduce the fourth one. Okay, so how about I can now call that P of x, okay? P of x, lowercase letter p of x. And here let's call that a -1/4, okay, of x squared. -1/4 of x squared. And so just like the earlier siblings that I've seen, it still has that its parents here. This function still has its parents here. And so now putting together as a relationship between this descendant and the parents, and now I notice this p of x here is the -1/4 coefficient multiplied with the parent function f of x that was previously defined here. That's how I'm seeing it. Okay, so now as another observation that I see, so this time I'm seeing this as, so -1/4 is a coefficient. That's being for sure negative. It's a negative coefficient. And now further, we notice that -1/4, okay, -1/4 is still greater than -1. Still greater than -1. Okay, but then in another way of seeing, and I highly recommend start seeing it this way, the absolute value of this -1/4 right here is still indeed less than 1. It's still indeed less than 1. Okay, and so now we're gonna start looking at the graph again. So the graph I'm still leaving on the screen here is not for this current one, and I will quickly adjust that. All right, so now in full screen view right here, let me hide away these points because they're no longer applicable. Okay, but now, and this is our graph of the original parent function. And so now let me all right, so now this is our descendants function. It looks like a fatter version again, but hold it. Let's put in the guiding points to really realize about what changed. Okay, so now on this graph right here, on the same grid line, x equals -1. Let's put in all of our points again. All right, so again, what we noticed, being a negative coefficient, for sure, just like the earlier problem, just like the earlier descendants j of x right there, having a negative coefficient multiplied to the parent function, it will cause the graph to be flipped upside down, being the mirror reflection of the parents through the x-axis. I could have also used this term right here when we were looking at the j of x earlier. Okay, so as I'm going along with the lesson here, you will pick up more terms and more terms that outside of me teaching it, other professors are using those terms as well. Okay, so you can think of this as a reflection of the parent's function through the x-axis, but anytime your coefficient is a negative coefficient, it's being flipped downward. Okay, and then after that, now the 1/4 being, you see, since due to the nature that the absolute value of 1/4, so now we're ignoring about the sign, but we're talking about the absolute magnitude, how big that scale is. So it's as far as the scale, it's still less than 1, and that's the reason why. That's what I explained for now in a closer look right here. Okay, then you see on the same grid, every y value on the parent's function, whatever that is, the corresponding point is only 1/4 of the way. So this one right here is telling the real clear truth right here. When x equals -2, for example, the parent function had the height being 4 for the y value of that particular point. Okay, but now it's on the same x value and on the descendants function, the y value only came out being a 1. And what I mean is 1 grid vertically pulled away, vertically away from the x-axis. That means that this distance here is only 1/4 as much. Okay, only 1/4 as much. All right, so now with all that observation we have seen, let's put it together again. It's flipped downward. Okay, the graph is flipped downward, and then every y value is only a quarter. Okay, it's only 1/4 of the original value right there. Okay, so now I'm gonna write down that observation. Every y value, okay, every y value is 1/4 times, only a 1/4 times as high, okay, compared to the parent function, or as high, and it's flipped downwards. Okay, so I'm only using the kind of language here that's understandable to everybody right there. So the height, I meant, and I demonstrated through the graph, it's only 1/4 times as high right there. Okay, being further away, being away from the vertically away from the x-axis, it's only 1/4 times as high. Okay, or as far, and I mean far away from the x-axis. Okay, that's probably more precise term. Only 1/4 times as far from the x-axis, and then the graph is flipped downward, just like that again. All right. So now at this point, we are ready for putting in some actual observation right here. All right. And so now putting all of that together. So I'm going to say, let f of x be a function, okay, or just a parent function. Okay. Now we're going to define g of x equals the parent function multiplied with a constant c, okay, multiplied with coefficient c right here. So this function will have the graph, okay, has the graph of f of x. But see, so now I'm going to start using my general term. So it's being flipped down, it's being the same way it is, but being stretched vertically up, stretched vertically down, or being compressed vertically and being pressed down, being flipped down and then compressed. It's all of that, okay? But then all of that together, I regard to that as, so the graph of f of x is vertically scaled, okay? The graph of f of x is vertically scaled. So I'm using that term right there, vertically scaled, because stretched, compressed, even flipped included. They're all just vertically scaled, okay? So they're vertically scaled as following. So now we're going to start splitting into a few situations right here, a few requirements, a few scenarios, okay? So vertically scaled, we're gonna say it's gonna vertically stretch. Okay, it's a vertically stretched. If the absolute value of k is greater than 1, because so now vertically stretched, I can see two ways. Either stretch in the positive way or stretch in the downward way. But any time that we're looking at that, vertically stretched means it's get farther away from the x-axis. Vertically stretched. If the absolute value, and allow me to correct this, I mean c. Absolute value of c is greater than 1. Okay, so allow me to clarify what I meant right there by absolute value of c greater than 1. So looking back at g of x, that was 3 times f of x. Okay, this value right here, I made that notice. I made that note about that earlier. So absolute value of the c. So the c is this value right here. This absolute value was greater than 1. So we did observe that this one here was a stretch. Okay, this one here was stretched. Okay, and then we came to h of x. We came to h of x, and it was a 1/2 f of x. And this, so the c itself right here was positive, similar with the g, but in the end, absolute value here is less than 1. So I saw this here as a compressed, okay, or being compressed, vertically compressed. That's not the case we're considering here in my writing yet, and we will get to this detailed situation later, okay? And then both of these two cases here, the c value is a positive c value, okay? And then in the case of the j of x that we investigated, okay, it was -2 times f of x. It was also this graph right here was also a stretch right there, okay? Or what we observed, absolute value of the c right here was also greater than 1. So these are the two cases I'm particularly focused to, okay? It's caused a stretch again, okay? It's vertically stretched. And then the case, I'm running out of word space, so I'm going to have to write it here, but the case for p of x, we had -1/4 times f of x, okay? And in this case right here, absolute value of that c is less than 1, and we will get to that as well. But that was also a compressed, but in the flipped down version, okay? And so now that's why back on my other board I was using the case when we notice the graph is vertically stretched, means being further out away from the x-axis. See, both of these two cases right here, the case on j of x and the case on g of x, that if you roll back on the video, that's what you notice. Both of these two graphs, once graphed, they are, all of those are on the same x value grid. The y values all came further away from the x-axis, okay? And that's why it's stretched, vertically stretched. All right. So now in that way, so once again, the g of x as a descendant function being defined as a coefficient c times f of x, it's going to be vertically scaled as the following. Scale as a vertically stretched if this absolute value of c is greater than 1. Okay, as you have seen in my extra clarification on the other board. And then further, so now I'm going to put a comma here, and then further, okay, and it's going to be flipped, okay, flipped downward. Allow me to use this daily language term, even though it's not too mathematically formal. Mathematically, they say that it's reflected through the x-axis. That's a more formal math term, but here, you know, comparing with the parents function, I see that as being flipped downward right here, okay, and flipped downward if c itself right here, not absolute value version, if it's a negative. So this is sort of like just a subcategory and an extra requirements only. So it can be vertically stretched and not flipped, or it's vertically stretched and flipped anytime we recognize that c is being negative value. Okay. All right. So we got one situation. So now I'm going to need to erase this and write the next the next setting right here. All right, and so now in another setting, it's going to be vertically scaled as vertically compressed. Okay, we're going to say it's vertically compressed. All right, if the absolute value of our coefficient is less than 1. Okay, and then further. And further. So that's next thing after the comma there, it's just extra if that happens, okay? And again, flipped downward, okay? If c is a negative value. So by default, if c is positive, then there's no flipped, that's all. And vertically compressed or stretch, vertically compressed or stretch, depending on the absolute value of your coefficient. All right, so that's how we putting these together and you know, systematize that, all of that. Okay, but then now when it gets to actually doing it, it's not always easy, because like I said again, just like how I was explaining about the vertical shift, okay, we were shifting up and shifting down. It wasn't so easy. It was not so easy. And especially now when I start writing down the formal observation there and putting that all together and to see all of that explanations, then it will become a little too much to keep track with all the little different details right there. Okay, it's vertically stretched when absolute value is above 1, and it's going to be compressed when it's less than 1, and furthermore it has positive or negative, making it flipped or not. Way too much information, way too much details, Okay, so when I was explaining about the the vertical shift, I also brought in some advice that's making it easier, because otherwise keeping track of all of these details, I mean, these are all the detailed explanation of what caused the vertical scales here. So we've seen through all of that, vertical scalings. Okay, whatever you wrote down, or anyone following with me here, and I had to erase out one of them because didn't have enough space here. But so we talked about vertically stretch, and then furthermore flip downward in that same case, and then vertically compressed still here. But these are all the different cases and scenarios for vertical scalings. But then just back to what I was in the middle of saying, really when applying these understanding will become when applying these the understandings, it will become challenging for a lot of people, actually. And at least that's what I've noticed in my teaching experience. It's not always easy to just, because the graph in the end we see it, but we cannot just hold it and stretch it out, or hold it and compress that. Okay, so it's not that easy. So there has to be some kind of advice that making it more solid, I mean crystal clear for students to visualize what it means by vertically stretched or vertically compressed or even flipped. Okay, and so now I'm going to leave this board. I'm going to get back to the other board. And this is now an advice that I once picked it up from my favorite professor, and then now I would like to hand it down to students who are studying with me right there, or anyone viewing this lesson and learning it from the lesson here. So when it comes to vertical scalings, and right now we're still talking about vertical scalings. So all of that details you have seen that I put together, really all of that can be explained all in just one statement right here, and making it all easy, surprisingly easy. Okay, so I call this an advice because it's not seen too often in many textbooks like that. So as an advisor here, anytime we're, for the case of a sibling function, I mean a descendant function being defined as a coefficient c multiplied with the parent's function. Okay, that's for this advice, the advice for this. So now I'm going to say, here's the following. I'm going to say in that case, compressed or stretched or flipped and compressed whatsoever, it's all about every y value. Okay, every y value is multiplied. Very strong statement. Every y value is multiplied by c. Once you follow this on every y value, you're done. And all of that compressed, all of that compression or stretch, or even compression and flipped, or stretch and flipped, they're all going to fall out just like that. Okay, they're all going to fall out just as a consequence of doing this. So this one single statement as an advice right there will work anywhere. We just simply multiply. So every value, every y value, nothing about the x, every y value is multiplied by c. That's how it happens. Okay, so now once we've caught that advice right here, at this point we are ready to start getting in. So you have seen quite a few examples already, but I did not put a number on those examples because those are a problem I brought up as example to lead into the understanding. But now I'm actually gonna show the examples to see, I mean to show you how you can apply your understanding into an actual problem when you're doing it. Okay, so there are so many different purposes of bringing up examples like that. All right, so now let's turn to the other board, and I'm gonna now write down my example number 3 right here. All right, so let's now look at example 3 in continuation with from the earlier the examples of the same lecture here. All right, so I want to say let f of x be represented by the given graph. Okay, so now let me first bring it up. All right, so that's the graph for this function f of x. So again, this is just the kind of problem where we don't know the rule of the, we don't see the rule of the function f of x written down, but we only see this rule already been, we only see this rule already represented by the given graph, and that's the given graph like that. Okay, and so now from that given graph that represents this function f of x, okay, then we are going to, we're asked to sketch the graph of the following function. All right, so now I'm going to start getting into part A of the example. So you can think of this graph that you are seeing here as the graph that represents the parent function. F of x is our parent function. So just like how I've been doing that throughout the lecture right here, now I'm going to call a descendant function, g of x. So how about our first one here in part A? How about g of x here is going to be, all right, so 3/2, okay, f of x. 3/2 f of x, okay. Sometimes the author can write, some author can write their textbooks as 3 times f of x over 2. Be aware of that, but that really means it's a coefficient 3/2 times f of x. Okay, so this way, may be aware, this way may be expressed in some problems, even though it's the same kind. So it's your responsibility to know that this form right here is exactly the same parent function, but multiplied by a coefficient 3/2 here. Okay, and so now, but let me erase this because we don't need to write that there. Just stay with what I wrote down. So 3/2 times f of x, 3/2 times f of x. So what I see here, this is a coefficient multiplied with f of x. So now I'm expecting, and just right out from what we freshly discussed, okay, we're looking at, it's going to do some kind of vertical scaling. So so at this point, anytime multiplying a constant coefficient to a function, simply just multiplying a constant coefficient to a function, it will for sure cause what's so-called a vertical scaling. It will cause a vertical scaling at this point. But then specifically, is that a vertical stretch or a vertical compressed? Is it a vertical stretch and flipped? Or is it a vertical compressed and flipped? Okay, we're going to find out like that. And so now, so getting into this, yes, we've seen all that. The coefficient here is a positive, so I'm expecting no flip. Okay, it's positive, so no flip. So just no flip because, or let me write it in short writing. So this is just thought process right here. No flip because the coefficient c 3/2 is greater than 0. So no flip. Okay, but then this 3/2 in absolute value is greater than 1. That means we know it's gonna be a stretch. Okay, it's a vertical stretch. So no flip, and then there's a stretch. Okay, so saying it by mouth is easy, but now how are we gonna do that on the graph, and particularly when we are not able to grab the graph and stretch it out right there physically? That's not possible for us because it's just on the picture right there. Okay, so when you're drawing it, so that's why, once again, back in when I was explaining about in those examples about the vertical shift, I already brought in that term using the guiding points, and I also mentioned that throughout my explanations about the vertical the scaling right here. All right, so let's see how the guiding point is going to help. So now right on this graph in a full screen complete view right here. Okay, so these are the guiding points. I mean, the reason I never formally explained about the guiding points is because it's just simply, it's not even anything formal. It's just those points that can be easily recognized right through the grid. Okay, so in this particular graph right here, we have a few points. Like say that point right here, right at the grid. Okay, that our eyes can see easily. And then that point right there, right at the grid, that point right there, that point right there, and that point right there. Okay, and those are good enough to be called the guiding points. That's all there is. So in that way, now let's look further into the graph. So with those, I'm now going to put the guiding points in. Those are the guiding points, and let's put in some label. All right, so that is the label. That is the label. So now I'm going to quickly observe that. So I'm going to do some scratch work. So I'm going to use this space. I'm still going to leave this as advice here, and I'm going to do my table right on here, because similar with the examples that we've done earlier, I introduced that table technique right there. Okay, and that was also my own technique that I formulated as my experience built when I was teaching this course for over the years. Okay, so I'm going to rely right on that on those guiding points that you're still seeing on the graph right now. So now similar to what I have done throughout example 1 and example 2 earlier, I'm going to make one column. I'm going to make one column to list down the coordinate values, or the coordinates, the pairs of values, right, from the guiding points here. So the first point from the left to the right, the first point I'm looking at here is a -3, -5. -3 for x, -5 for y. Okay. The next point to the right is a 1, 3. Okay. And then the next one to the right is going to be, how about 5, 3. Okay. And the next one to the right. The next one to the right is 8, 0. And you are, and for anyone viewing the lesson at the same time, you are also seeing this at the same time with me. Okay. And then the last point on my list here, and it doesn't have to be, and all of that explanations about why it's useful to use these guiding points, I've had all of that explanations back in the earlier example. So it's the same exact philosophy right here. So 11, 3 is the last point right there. Okay. So now these are the y values. Okay. So now this advice, the reason it became an advice because it's so useful. Yes, formally it was whatever I wrote on the other board and I erased. But now this advice right here works anywhere and make it fast, solid at least. Okay. Every y value is multiplied by c. C in this case here is the 3/2 in our problem. This is c. Okay, in our problem. Because our function here is a 3/2 times f of x. The parent's function is here. So c is this 3/2. Okay, so far I wrote down all of that observation right here, and all of those are predictions based on the observation. Okay, but now when we actually getting into doing that, okay, stay with the advice. So now that means I'm going to create in my next column right here. This is f of x, but this is going to be the transformation after multiplying f of x by 3/2. Okay, so this is what's going to happen. And so in blue ink for my descendant function, this is for g of x right here. -3 stays the same because it's x value. Nothing stated about the x value in this statement right here. So keep it the same naturally. But then the y value, we multiply the y value. Every y value is multiplied by c. Now it becomes a -15/2. That's how it's done. Okay, 3/2 multiplied with -5 gives me a -15/2. Okay, and I hope for this class right here, nobody need to have extra explanation about how that arithmetic came out from. Okay, and then now for this pair right here, 1 is the x value, stays the same. 3 times 3/2 gives me 9/2. Okay, and then moving on to the next one right here, 5, 3. 5 for the x value stays the same. 3 times 3/2 gives me 9/2. Okay, all right, and then 8, 0. 8 for the x value stays the same. Okay, but 0 on the y value is multiplied by 3/2, which is also 0. So 0 times 3/2 is 0. 0 multiplied with any value is 0. Okay, and then 11 stays the same. 3 multiplied with 3/2 gives me a 9/2. All right. So this is my point. This will be my guiding point for the transform graph of the g of x function right there. All right. So in that way, let's see how it works. Okay. Let's see how we can bring it into our actual function here. So, all right. So on my actual graph now in full screen view right here. All right, so now these are the guiding points. Okay, so that point is corresponding with this, that point is corresponding with this, but wait a minute, some point is missing. It's actually down here, and this is the reason why having technology can be a good gift sometimes. Okay, so now I see this point, I see that point, okay, I see these points corresponding to that. Okay, so if we can check, so now once again all of these points are supposed to stay in the exact same x value grids, okay, with its parent point right there. All right, so this red point was absent because it's hidden behind the blue point right here, so even the transform version is still there. So the idea now is that, and as I have already mentioned, it does not matter what transformation we're doing, okay? But it will not change the shape of the graph into a completely different shape. So right here in the way how I'm seeing, at least, and now another advice from me, anytime that you're learning to do anytime that you're learning your steps, building your experience in doing these transformations right here, learn that skill to, look at the parent's function and then close your eyes and still imagine that shape is still there. So if I close my eyes here, and then that shape is still this shape right here, going up, going flat, hop down as a bowl right there. That's a shape, okay? Have that nailed down in your mind somewhere, in your imagination somewhere. Because now once you have applied, after you have applied any transformation, it's still gonna be that shape, going up, going flat, and there's still kind of like a bowl shape after. At least that's the shape fundamentally being represented in this graph right here. So I am expecting the exact same kind of situation there. Okay, so in that way, now let me show the actual graph. All right, so now at this time right here, I'm going to put it in complete full view, full screen view, and then allow me to draw the graph as close to how we're doing a hand sketch as possible. So with all of these, so the first thing is to put down all of these transform guiding points, and now we're gonna draw the graph through these connecting these transform points right here. Okay, so and trying to maintain the shape. So now from the left to the right, here's how I'm drawing it. All right, so that's how the graph is done, and then so that's the first segment, and now it's gonna turn over to the next one, and then it's gonna bend as a bow curve, as a bow shape right there. And that's how we complete our graph. All right, so now I am going to, for now, hide away the graph in red so that we can clearly see the transformed version. Even though already being transformed, it still carries that exact shape. It didn't turn into like a loop. It did not turn into a rectangle. It stays exactly the same shape right there. It's just being scaled differently. Okay, and now that's what it means by a vertical scale, because now putting back the original graph right here, you can see that the blue one here is the same exact shape, but it's just being stretched, vertically stretched, so it's consistent. It's all consistent with these observations we've made right here. There's no flip. There's no flip because it's positive value. Okay, but then the constant coefficient was in absolute values greater than 1, so we were expecting a stretch. It's all there now. After taking that advice, the work went extremely quickly, and we got solid method. We got the crystal clear method to put the points on precisely at the right place to draw the graph successfully if we had to do that by hand. Okay. All right, and now with the same graph, being the parents function. Let's look at part B right here. Let's look at part B. All right, so part B of our function, of our example over here. How about I'm going to look at g of x being a descendant function that's defined as, how about negative 1/3, okay, negative 1/3. F of x, negative 1/3. Okay, so the graph of the parents function is still here in our board right there. But we now want to sketch this graph. And the point now is that we're doing, so I have to use computer to do the auto demonstration, but I'm trying to mimic the idea about if we're indeed doing that as a hand sketch version. So these are intended for you to do as a hand sketch, okay? Because that's where you can actually apply your understanding. So as a hand sketch, let's sketch this one right here. Let's sketch this function right here. It's negative 1/3 times f of x. So sometimes alternatively, textbooks can write this as a minus f of x over 3, okay? Just for you to be aware. But then since I didn't write it that way, now I'm going to erase that. Okay, just for you to be aware that there will be times it will be written like that. We understand that as negative 1/3 f of x. So now writing it this way, we clearly see this is constant c right here. So our c is a negative 1/3. So it's now less than 0, negative value. So at least 2, we know that there's going to be a flipped. We're expecting it's going to be flipped downward. Okay. And now it's becoming more clear and more clear how all of that understanding we've learned earlier apply. Okay. We're expecting that it's going to be flipped downward. All right. And then furthermore, this c in absolute value, negative 1/3 in absolute value. It's a 1/3 in absolute value. It's a 1/3 positive, so it's less than 1. The absolute value of negative 1/3 is less than 1. So in that way, I'm expecting, even though I did not put in the graph yet, I'm expecting that it's going to be compressed. Okay, it's a vertical compressed or vertical compression. It's vertically compressed. All right, vertically compressed and also and further being flipped downward. So think about that same shape, we're going to flip it through the x-axis. Okay, and then as after we flipped, or you can compress first and flip. There's really no the preference about the order of doing these. There are really 2 transformations apply in these. Okay, anytime we do a vertical scaling, there can possibly be 2 transformations being in one. Okay, so now let's handle that. But so in the end, see, putting the details of the 2 different little transformations together can become challenging for somebody. So stay with that advice I had on the other board again. Okay. So in the advisor, and this is the work from the earlier problem. So let's erase it out. Okay, and I shouldn't erase these, but then I'll quickly spend some time redrawing those. But this advice says anytime we're doing this vertical scaling right here, all we have to do to keep it easy for us, stay focused on the guiding point. And then every y value is multiplied by c. This is actually true for all y values. But that's the reason why we chose to work on the easy guiding points. Okay, so now in this particular example, part B, problem B right here of example 3, the c value is a negative 1/3. Okay, so here's the set of guiding points from my original parents function. First point from the left to the right is a negative 3, comma negative 5. All right, -3 comma -5. And again, let me put that in full screen view with the guiding point so that everybody can see it more clearly. All right, so those are the one. Okay, -3 comma -5, 1 comma 3, 5 comma 3, 8 comma 0, 11 comma 3. Okay, all of those. All right, so now allow me to get back. So that's my complete list. And now on this table, for the next column to the right hand side, this is what I'm filling in right here. All right. And what I have here is -1/3 f of x. So our c is -1/3. All right, so that tells the story clearly at this point. I'm going to multiply every y value by -5. I mean by -1/3. So this first pair, x value is -3. It stays the same. This y value is going to be multiplied by -1/3. -1/3 multiplied with -5 will consequently give me +5/3. And you can double check with the math here, but I highly believe anyone is at this point is comfortable enough with multiplying fractions and values. Okay, and so now the next one here is 1 comma 3. 1 stays the same. 3 is multiplied with -1/3. So now we have 1 comma -1. Okay, because 3 times -1/3 gives me a -1. Okay, the next point down, 5 stays the same because it's x value. 3 times a -1/3 gives me -1 again. Okay, -1. And then 8 comma 0. 8 stays the same. Okay, 0 is multiplied with -1/3, but wait a minute, 0 times anything is 0. So it seems like that point stays exactly the same spot. Yeah. All right, so don't worry about it. Let's keep advancing. So 11 comma 3. 11 will stay the same because it's x value. But now 3 times a -1/3 gives me -1. That completes my list of the guiding points on the transform graph. Right there, on the transform graph. See, on the graph of g of x, -1/3 times f of x. All right, so let's now put it in. So now I'm going to get back to my graphing space right here. So on the graph, these are the guiding points. Okay, these are the guiding points. And so now, this time I'm flipping it. So we're still going to connect. So as we connect, we will start seeing things a little better. So these are the guiding points that reflects -1/3 times the f of x. So you can see that this original point is -5 was the y value, so now it becomes a 1. I mean, it becomes a 5/3 right there, which is numerically 1.66666. Okay, because it's only 1/3 of the way compared to this. 1/3 of this. This point is being vertically away from the x-axis about only 1/3 times compared to the original parent function. And then it's even more clear here. On the original point on the parent function, it's 3 grids away, vertically away, and here it's only 1 grid away. Okay, it's compressed. Okay, so 3 grids away on the parent's function. Now on the descendant's function, it's only 1 grid away, and then it's now, when it was a parent's function, it's going up. Here it's sinking below the x-axis because it's flipped. Okay, so now we're gonna just think about connect. So between these 2 points, it has to be a straight line, just like that. Okay, so I'm gonna start connecting. All right, so now I'm gonna connect. All right, that's just like how it works so far. So connecting. So this is the transform piece compared with that first piece right here. And then I'm gonna continue further. All right, so now I'm expecting another segment right here, another flat segment. But this is the transform version versus that original one. And then from here through all these 3 points, I'm expecting a bow shape right here. Okay, a bow shape, but this time no longer pointing up. The bow is going to have to be pointing down like a dome right here. Okay, so now that's what it is. Okay, and that's the end of our graph right there. So this graph right here that you are seeing is the graph that reflects -1/3 negative 1/3 f of x. Okay, all right, so now before we leave this example, I can put in an FYT for anyone to try, okay? And so the whole idea about an FYT, so try it on your own, make your own sketch. So the point now is that I'm only using the technology to show, to be as close as how I'm doing a hand sketch, because I love to show I'm embarrassed myself to draw my own hand sketch version because I'm not confident, okay, in terms of the precision. But now you are students, you're on your way learning, feel free with that. I mean, be okay about that, okay? So do this on a hand sketch and then compare with my version on the graph right here. So a little bit upscale is okay, completely okay. We're not racing with machines or anything like that. So as an FYT, all right, I want you to do for me, how about g of x is a minus 2 f of x, okay, minus 2 f of x. All right. All right, so this is now the answer. This is f of x minus 2 times f of x is the following function. In blue, minus 2 times f of x. This is the function. And allow me now to put in the guiding points right there. Okay, and so again, the whole idea about these FYT problems is that I don't need to show too much reasoning for that any longer. So these are the guiding points, okay? And then you can compare with your own work. You can compare with your own work about how these guiding points should be consistent with your own calculations of the points. All right, so that's how you have done a transformation independently on yourself, hopefully. All right, so let's now get ourselves into another class of problems right here through example 4. All right, so now I'm going to spend some time writing down the instruction, the worded instruction of the entire example here. All right, so example 4, we will be sketching. So, and again, entirely as a hand sketch, okay? So we want to sketch the graph of each function. Okay, sketch the graph of each function by recognizing it as a transformation of a known function. All right, so as a transformation of a known function. So the idea of this example is very similar to the idea of that example in example 2 that we have done earlier in the lesson here. So we want to do a hand sketch of the graph, but to make it easy for us, I don't need anyone for any of these hand sketches right here. I don't need anyone to do plot by points to eventually draw the graph. That's too much, okay? The worst thing is to pull out a graphing device and just type it in whatever the function I'm giving here. So that's you lost all that points about learning, okay? But the idea now is that whatever function I'm about to give, I want you to recognize the function as a transformation of a known function, okay? So in any of the function I'm about to give here, there will be a known function, okay? That's, and known means you already know the graph of that known function. And that's why the idea is very similar to the example we have done back in example 2, of those problems we have done in example 2. So let's get to it. All right. So what about in part A? Let's now graph our function g of x equals, how about 3 square root of x. All right. 3 square root of x. This is the function that we're aiming to make the sketch for here. That's the main function of our intention. But now, you see, we don't want to build table of values. We don't want to construct table of values. Like when x equals 0, output equals whatever. When x equals 1, output equals y equals whatever. And then we're going to trace the points and then get the graph. That's not the point of the problem. And again, like I said earlier, the worst is to input this into a graphing calculator and get it done. Well, that's machine doing that for us. That's not what our work. Okay. So the point now is that I want to see this as a transformation from a known function. Okay, so what known function can I see in this problem right here? So observation tells me that this is, in this function overall as a function, the operation is stating the following. It's 3 times. Between the 3 and that square root right there, even though not written, but there was a multiplication, there was a product. It's a product between 3 and the square root of x. Okay, so that means 3 times square root of x. I purposely wrote it out a little more separate right there. So now this is what I recognized. This is what I recognized. This is my known function right here. This function now is known. All right. That function now is known. So now that known function, how about let's now call that f of x. Square root of x. So how do I know so sure that I know this function f of x equals square root of x? This is simply because this is one among the toolkit functions that I have introduced prior, a few lectures before we stepped into this particular lesson right here. All right, so again, go ahead and review. If you're not sure about this function, go ahead and exit out of this lesson and review your toolkit functions, specifically on this particular one right here. At least you need to understand the graph of this toolkit function. Okay. All right, so now on the empty graphing space, this is our graph for the square root of x. And so in case you didn't review the graph for square root of x, this is what it is again. Okay, and so but at this point I consider this function here as a known function. It's a known function because it's among the toolkit functions. So any further details allow me to assume you already know. Okay, so now I'm going to put in the guiding points, because to make it easy, stay with the guiding points. That would be our best shot to get these problem pulled out right here. All right, so the guiding points are here. Just simply pick on those points that stays right on the grid. Okay, so that point. And now let me put in the numerical label of those guiding points right there. Okay, so now apparently they stay right on the grid. All right, and then or let me also put in another one. So how many guiding points are good enough? It's really up to your own preference right there. Okay, and again, that's why I was explaining earlier, the whole point of these guiding points is that we just simply choose those easy points that stay right on the grid, but they are useful in a sense that they define the shape of your graph. See, so if we're tracing through the shape of these guiding points right here, at least, okay, even if we are the worst artists ever, we have to form into that nice curved looking shape right there. And that's the one, and that's the whole point of introducing those guiding points right there. Okay, so now with the guiding points having the coordinate values being displayed there along the way, so now let's look at on my board here, I'm going to construct the same usual work. What I recognize here, okay, and now I need to erase out, I need to clear out this particular board. So in a way how I recognized our function earlier, okay, f of x, or actually g of x here is positive 3 times the parent function times the known function. Okay, so that means we observe that the c here is a 3. Okay, and so I'm expecting. So let me get back to my other board. Okay, I should use the other board right there. So see, this is the c value. Okay, so in that way, I see that g of x equals a constant 3 times our known function, where we treat it as a parent function. So c is a value being 3. Is that value being 3? So c is positive for sure. So I'm expecting no flip. Okay, no vertical flip. And of course, the kind of problem here that we're still looking, we're still learning, we're still studying about vertical scaling. So needless to say, any of the transformation we're about to recognize here has something to do with the vertical scaling. Okay, so now since C is apparently positive, so there's no flip expected. Okay, C is, well, absolute value of C is greater than 1. So I'm expecting a vertical stretch. Okay, vertical stretch. All right, so that's all of the expectations. But then putting all of those together, when we're actually graphing it, it's going to make it hard. It's not that easy, okay, to say it by mouth. I mean, it's not that easy to get it done on the papers, even though it's so easy to say out through the mouth like that. Okay, so that's why I once again stay with the advice. So on this board right here, now once we've recognized all that, then with the C being 3, okay, we know that the C being 3, then all I need to do is, and once we already had the guiding points is still being shown on the graph right here, then every Y value is multiplied by C. Doesn't matter if C is positive, C is negative, and you have seen all that through the earlier examples. Doesn't matter if C is positive or C is negative, one C is known. Multiplying C will bring the point to the exact place, okay, as expected. Okay, so that's why now again I'm doing that table approach. So here's my table. Okay, the first column is for the original parent function. So these are the points. So the first point on my graph here, and you're still seeing it 0, 0. The next point to the right hand side is a 1, 1. And the next point to the right hand side is a 4, 2. The next point over is a 9, 3. And the next point over is a 16, 4. Okay, so those are all of the points, the guiding points originally. Okay, so now 0, 1, 2, 3, 4, those are the Y values on the guiding points. So now with this transformation, right, the advice set, we just simply need to multiply C to every Y value, or every Y value is multiplied by C. All right, so now we are ready. That gives us a very clear instruction right here. All right, so now for g of x, which is 3 times square root of x right here. Okay, 3 times f of x, or maybe I should have written 3 times f of x instead of 3 times square root. Okay, so 3 times f of x. So now 0, 0. The first value is 0, doesn't change because it's the x value, stays the same. But the second value is a 0. Now multiply with the 3. 0 multiply with 3. But wait a minute, it's just 0. Okay, so I have another point being 0, 0. All right, but this point now is on the descendant function. All right, so at this point we are already moving on right here. 1, 1. 1 for x doesn't change. It stays the same. 1 right here for the y value, that will get multiplied by c, which is 3 in this case. So 1, 3. Okay, 4, 2. 4 is the x value. It doesn't change. It stays the same. Okay, but now 2 is multiplied by 3, which gives us 6, because once again every y value is multiplied by c. So of course, needless to say, the y values here are multiplied by 3. So now I can start picking up the pace a little bit. Okay, so the next point gives me 9, 9. Okay, and the next point down is a 16, 12. All right, 16, 12. So all of these y values are multiplied by 3. Now we can put these final guiding points on the graph, and later, see, I'm writing that in blue ink right here. So expectedly, when I'm putting these on the graph, I'll use blue. If you have color pencils or anything like that when you are attempting to do these, otherwise, you're probably gonna just need to spend a harder time, slightly harder time to recognize between the original parent function and the transform version. That's all. Okay, so let's see this through the graph. All right, so now these are the guiding points. Okay, these are the guiding points for my descendant function. All right, so I had to drag my graphing window a little bit down with decimals here to show the complete of all the points, the complete set of all the points. So the first guiding point is here on the transform version. The second one is here. And see, so let's look and check for consistency. And the y values here are all consequences of multiplying the original y value by 3. So it was y equals 1 on the parents function, now it's y equals 3. It was y equals 2 on the parents function, now it's y equals 6, and so on and so on. Okay, and so now it's time to put in the actual graph. All right, so let's look at the graph now. All right, so there you go. So if I'm using a hand sketch, that's how I would sketch that. I would sketch from the left to the right. Okay, and all right. And so that's how I would continue and keep making the graph further and further. All right, so that is the graph of this blue graph right here is the graph of g of x equals 3 times square root of x. Okay, where I recognize that this is a transformation from that known function. So this was the known function. Okay, this one right here, that was known, because we knew it from our learning about all of those toolkit functions. All right, so now again, after so much explanations about the steps here throughout part A, so I'm going to put in part B again for viewers to follow along, and I can show my thought process, but I can start picking up the pace here. Okay, so here we go. All right, so for part B right here, let's look at how about g of x defined as negative 1/4 of cube roots of x. Okay, so negative 1/4 times cube root of x. All right, so aka this function is also written as negative cube root of x over 4. Okay, some different expressions of that, but same function. So we'll stay with this so that we can clearly recognize. All right, so now here's how I see it as a thought process. The problem is asking us to recognize this as a transformation of a known function. Okay, transformation on a known function. So this function here, I recognize what I recognize. F of x equals the cube root of x. That's what I recognize. Okay, and f of x equals cube root of 9. The reason I recognize that because it's among our toolkit functions. Okay, so this is known. So now I see this overall function g of x here as simply just a constant c, a constant coefficient, negative 1/4 times the known function f of x. That's how I'm seeing it. All right, so I have all that tool I need now. So the c here as another thought process, the c is a negative 1/4. Okay, so having the value, the information about the c here, the constant coefficient being addressed here. Now I'm going to say, since c, think about that, since c is negative, right? I'm expecting, consequently, I'm expecting the graph of the transformation here is going to be flipped downward. Okay, it's going to be flipped downward. Since the absolute value of c in this time is absolute value of negative 1/4, which will be less than 1. Okay, so I'm expecting a vertical compression. Okay, it's a vertical compression. All right, but then putting both of these details together will become hard. So I'm going to stick with that advice again. All right, so now with g of x recognized as a negative 1/4 of f of x, right? The advice says, and of course we already addressed that c is negative 1/4, and we recognize all that property. So every y value is multiplied by c. That means every y value is multiplied by negative 1/4. That's the part that's really gonna make it precisely clear. Okay, and so now let's make a table of values for the guiding points right here. I mean the table of coordinates values, okay, of the guiding points. But let's show the graph of the original function first. All right, so this is the graph of the, this is the empty graphing space right now. All right, so now let me show the graph of the cube root function. All right, so let me now show the graph of the cube root function. This is the graph of the cube root function. Okay, so this graph in red right here. So now let's recognize the special guiding points. I see one is right here at 0, 0. I see one at this point, and I see one is down here. So at 1, 1, at -1, -1. I see another one at 8, 2, and at -8, -2. So let's put in those points right there. So now these are now the guiding points, just as said, and with these being their labels, their numerical labels. Okay, and so now with these guiding points, I'm now ready to make my table. So as far as the calculation, this is the part we can do right here manually. Okay. So on the table, a column for f of x with the original points. So we're looking at -8, -2. Okay, I'm looking at another point being -1, -1. I'm looking at another value being 0, 0. I'm looking at another point being at 1, 1. I'm running out of space a little bit, so allow me to extend my table to this side right here. So as a continuation of our table. So here there's 8, 2. All right, and so now once we've had the coordinates for all, at least some list, right, of all of the guiding points are here. Now we are ready to calculate the transform guiding points. So now -1/4 times f of x is going to give the following list. First pair of values, -8 stays the same because it's x-axis. Because it's x value. So -8, but -2 multiplies by c, multiplied by -1/4. So that becomes a positive 1/2. Okay, -2 times a -1/4. Okay, it's a positive 2/4, which is 1/2. All right. For the next pair, -1 stays the same because it's x value. -1 times -1/4 is a positive 1/4. Okay, and then 0, 0. X value stays the same. Y value is multiplied with -1/4, but 0 multiplied with -1/4, it's just a 0 again. Multiply with anything, it's going to be a 0. And then 1, 1. So x value stays the same. 1 multiplied with -1/4 is going to give me -1/4. Okay, and then this last point right here, 8, 2. 8 stays the same, and this is -1/4 times f of x. So 8 stays the same because it's x value, and now 2 times a -1/4 gives me -1/2. Okay, -1/2. All right, so that completes our guiding points on the transformed version of the original graph. Okay, so let's have a look. Let's put it all together here. I'm going to put all of these points, these blue guiding points, on the graph. Okay. So now on our graphing space right here. All right, so these are the guiding points. Okay, these are the guiding points with the coordinates plugged in right there. These are the guiding points. So if we're looking at that relative to, if we're looking at these relative to the parent's point right here, then you see this one right here has that point being the flipped version, okay, being reflected through the x-axis, and only a distance of only a 1/2. Well, so compared to this distance, it's actually on the parent's point, the y value, it was 2 square grids vertically away from the x-axis, but now it's only a 1/2 square grid vertically away. So that means it's 1/4, it's 1/4 of the total distance that expected here. Okay, and here it's only a 1/4 out of 1. Okay, so clearly it's a ratio of 1/4 like that. Okay, and so now after looking at those guiding points, now it's time to put in the actual graph right now. And so now it's still going to need to maintain this bent curve right here, but then it's in the flipped version, and you can start seeing already that these are in the flipped version. All right, and your eyes can tell it. So now connecting these in a bent, as if we're doing a hand sketch, don't worry about if we can make it a precise one, be as close as possible. That's all. Okay, so here's the hand sketch of that. All right, it's a hand sketch of that graph right here. So the graph in blue here now is our graph of the function g of x equals negative 1/4 cube root of x. Okay, all right. So now before I'm leaving this example 4 right here, let's look at an FYT right here. And so again, the whole idea of an FYT for your own trying is that I can just simply write down a problem, and you will go ahead and apply what you have learned and doing that on your own independently. And then I will just simply point out the final answer. All right, so for this FYT right here, let's look at g of x equals okay, so I'm purposely writing it this way. G of x equals minus 2 over x. Okay, and this is the same as g of x equals really negative 2, okay, times 1 over x. So this is about the furthest I can tell about regarding the information. You will go ahead and recognize the known function on your own. Okay, and then I will just simply jump back in and point out the graph. All right, so at this point, after hopefully you have have spent some time working on that, right? Let me now show the graph. All right, so now again on my empty graphing space right here, this is the graph for 1 over x. Okay, and the reason I bring up this 1 over x because so now as far as just simply an answer, I can tell you that known function to be recognized is the f of x to be 1 over x. Okay, and then anything else I expect you to get it done on your own independently. So f of x equals 1 over x. This is the known function. It's known from the toolkit functions. Okay. And so again, this is the graph for the toolkit functions. And now these are the guiding points on this toolkit function. Okay, and I can zoom them in pretty close. All right, so now this is now the graph of the transform function. Okay, this is now the graph of the transform function, and then so now in a zoomed out version. And now in a zoomed out version, this is what it looks like. So it is flipped from the original graph, and these are all the guiding points right here after successfully calculating them.